So today I'm going to be explaining how to turn an enol into a ketone through a ketone-Enol tautomerization. So first I just wanted to take a minute and explain what our enol is. So our enol, which is shown on the left side here, is simply an oxygen that is directly bonded to a double bonded carbon. And then over here we're going to be turning it into a ketone, which is an oxygen that is double bonded to a carbon and has two other groups. In our molecule, the two other groups are going to be carbons. So let's get started. The first step in our mechanism is going to be deprotonation. Deprotonation is the removal from a hydrogen from a molecule. In this step, we're going to be removing a hydrogen from our oxygen. This is going to take place through the addition of a base. Our base in this step is going to be sodium hydroxide. Now, I only have written the OH portion of sodium hydroxide because Na plus is only going to be a spectator ion and it's not going to have a key role in this mechanism. So to get started, we're going to take the lone pairs and we're going to come up here and grab our hydrogen from our oxygen. This is going to take place through the bond breaking, and when the bond breaks, the oxygen is going to gain another set of lone pairs. This is shown in our products, where the oxygen now has an extra set of lone pair where it originally had two. We have also formed water, and this took place as our oxygen came over and took the hydrogen. Now for step 2, protonation. In this step, we're going to be making two products. But first, I want to explain what protonation is. Protonation is where a hydrogen forms a bond to another molecule. In this step, this is going to be taking place with our pi bond. Our pi bond is going to come over here and grab this hydrogen from our water molecule, which was formed in our previous step, and form a bond attaching it to our molecule. And while this is happening, the bond between hydrogen and oxygen is going to be breaking, and when the bond breaks, our oxygen is going to be gaining another set of lone pair electrons. And this is shown over here, where instead of having our water molecule, we now have a hydroxide, OH-, and where there previously was a hydrogen bonded here, there are now a set of lone pair electrons. And then for our other product, our hydrogen, which was attached to our water molecule, is now attached to our third carbon. And on the second carbon, there is now a plus sign, indicating that our carbon has turned into a carbocation. Now, let's move on to our last step. Before we move on to our final step, I just wanted to take a minute and explain why I added the hydrogen to this specific molecule. So, as explained in our previous step, this hydrogen was attached to a water molecule and we separated it by breaking the pi bond that was here. And in its place, our hydrogen was attached to this carbon. I attached it to this carbon to ensure that our carbocation took place at this center. And I did this because I wanted to ensure that our molecule had the highest stability where our carbocation was going to be, and also to aid in our final step. So to do that, I had to add the hydrogen here, and then this carbon no longer had a full octet, which made it a plus sign. So now we can move on to our final step. Now on to our final step. This step can actually be shown in protonation, but I think it's easier when explaining this whole mechanism to spread it out and explain what each part is. So, in this step, the lone pair of electrons on our oxygen, it's going to come down and form a bond to our carbon. In doing so, it's going to remove this plus sign, removing the fact that our carbon was once a carbocation, and it's going to not only fill the octet for this carbon, it's also going to satisfy our oxygen. Now our product is going to be a ketone, which is simply an oxygen that is double bonded to a carbon and then two groups. And this is the end of our mechanism. We have officially converted an enol into a ketone.